Right. Right. Okay. We'll start. We'll start. Right. All right. Good afternoon. Good afternoon. First, can you confirm whether I'm audible? Audible, right? Okay. Sometimes colors might be a little bit different today uh, compared to other days because some of the lights and the curtains are changed, right? I don't know whether it's affecting the colors. Is there anything else? I mean, anything like that? For me, I think it's not that noticeable. Is there any difference from your end? So you also didn't notice any change. Okay then. Right. Okay, let's start. Let's start. Good afternoon again. So as we planned last day, today we will be starting our next part in thermal, that is calorimetry. That is calorimetry. Right? We'll be starting the next part, calorimetry. Right? And the other things which are coming up on the week are tomorrow means Friday. Tomorrow we'll be having the S2A discussion at the usual time. Right? We'll be having the S2A discussion at the usual time from 8 to like somewhere around 9:15, 9:30. Right? And for tomorrow also, my plan is to discuss more vectors and force equilibrium questions. And since surface tension and viscosity are also finished in our reverse class, right? Since they are also finished in our reverse class, I'll be allocating two S2A sessions for surface tension and viscosity question discussions as well, right? And yes, other than that, on the reverse class on Friday in the reverse class, we will be starting elasticity this week, right? We'll be starting elasticity. So we are now in the last parts of properties of matter, right? We are in the last parts of properties of matter. So we will be starting elasticity this Saturday in the reverse class, and after elasticity, the next unit to be started in the reverse class is matter and radiation, right? That will be the main lesson we will be covering in this month, right? Matter and radiation. Okay, so those are the things. Yeah, I think about paper writing also, it's going on. And this week you are having paper 9. Paper 9 from the beginning of the class. Since the beginning of the class of paper class, you are writing paper 9 part 2 this week. Okay, right. Then without further ado, let's move on. Okay, take down the heading as calorimetry. 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 Right. Give me one more second. Okay. All right. So I thought something is on the lens of the camera. I think now it's fine. It was a small dust particle. That's why. Small dust particle. Okay. Calorimetry. Listen. Listen. Tell me. Now, let's break this down. Let's break this down. Calorimetry. Right? Calorimetry. Then here, see, this is about calories, calorie plus metry. Okay, first tell me what is the meaning of the word metry in English? What is the meaning of the word metry? Metry in English. Metry. What's the meaning? Anyone? It's kind of a popular word that we are using day to day sometimes. What's the meaning? Metry. Anyone? Meaning of the word metry. Metry. On thermometry, calorimetry, hygrometry. Right? So like what is the meaning? Metry. Anyone? Some of you are on YouTube as well. So anyone on YouTube or Zoom? Metry. Any idea? Any thoughts? What's the meaning of the word metry? Oh, where do you have come across the word metry? Any place where you have come across the word metry? No? No? No. Right. Metry means measuring. Right? Metry. The word metry means measuring. Metry means measuring. Metry means measuring. Measuring or measure. Measuring, measure. This is the idea. Right? So what's the meaning of calorie? Calories. Calories. Calorie. What is the idea? Calories. Calorie. Huh? That you should know. It's more popular compared to metry. Burning calories. Calorie levels. Right? Is the video stuck? One more second. Now it's fine, right? Energy. Moshe, the unit of energy. Correct. Idea is there. Idea is there. Listen. Idea is there. Calories refers to energy. That is true. Calories refers to energy. Right? Calories means energy. Right? Calories means energy. Listen. Calories means energy. Right? So, especially in this lesson, This is not about not just an energy, not about just an energy, right? So in this lesson, that is about heat energy. In this lesson, that is about heat energy, right? Energy means there is heat, right? So under this lesson, that is about heat energy, right? So simply now if I break this down, calorimetry into these two, so it is going to be all about measuring heat. It is going to be measuring heat. Measuring heat in the sense, measuring about heat transfers in the sense, maybe heat liberations, absorptions, emissions, right? So likewise, the study we do to measure amounts of heat transfer. Listen, the study we do to measure amounts of heat transfer is called calorimetry, right? So keep this in mind because there are more metries coming up like hygrometry, thermometry. So even within this lesson, we have several metries, right? Any metry means measuring. So this is about measuring heat transfer, measuring heat transfer. Write down below, write down below. Write down. Calorimetry is the study on. Calorimetry is the study on. Write down. Calorimetry is the study on. Calorimetry is the study on amount of. Calorimetry is the study on amount of heat transfer. Calorimetry is the study on amount of heat transfer. Calorimetry is the study on amount of heat transfer. Amount of heat transfer. Right? Okay. To get here. Listen, there are three possible ways. There are three possible ways, only three. There are three possible ways that we can write amount of heat transfer. Right? In physics, there are only three possible ways that we can write the amount of heat transfer. There are only three ways, and these three ways are for like exclusively for three different cases, three different scenarios, right? And some of the equations from here you already know because in O levels also up to some extent, some calorimetry parts are there up to some extent, a certain extent, right? So therefore, you should know this equation. I mean, you have come across and you should have heard these equations from O levels as well, right? Anyway, I'll be explaining everything from scratch, right? But I know most of you might have heard these equations as well. Right, don't write, just look at the board. Don't write. There are only three ways that you can write the amount of heat transfer. One is as ms theta. One is as ms theta. Right? Sometimes you might have seen the same equation as mc theta. Right? Mc theta is now obsolete. That is kind of expired. Right? We don't use S. We don't use C. We use S instead. Right? And then Q equals C theta. And Q equals ml. Q equals ml. Right? For these three equations, they have their own specific users. They have their own specific users. Right? Otherwise, each and every equation cannot be used everywhere. So therefore, they have their specific users. We'll see what the specific users are and the introduction and everything. Right? These are the only three ways. Listen, these are the only three ways that we can write heat transfer. Right? Either as ms theta or c theta or ml. Right? Now this is like this. Don't write. This is to determine. This is to determine heat transfer. When S is called specific heat capacity. This is when specific heat capacity is given. This is when specific heat capacity is given and C is heat capacity. So that is when heat capacity is given. And this equation is only for dedicated for state changes. This is dedicated, this is only for state changes. So likewise, they have their own users, right? They have their own users, right? First, take down the equations and the thing we are going to write here, I will say it, I will give it, right? Don't write these three, write the equation, and in front of the equation, keep around 2 to 3 lines to write something, right? Keep like 2 to 3 lines here to write something in front of the equation. Okay, write down equations, take it down. Q equals ms theta, Q equals c theta, or Q equals ml. Has the rain started again for your areas too? Here it's raining. Like from 2-3 days now, it's raining here. Be careful if you are living in a vulnerable area. Okay, write down in front of the first equation here. Write down in front of the first equation. In front of the first equation, write down. And use a red pen. Use a red pen and write down in front of the equation. Use a red pen and write down in front of the equation with an asterisk mark. With an asterisk mark. Write down. To determine. To determine. To determine. To determine amount of heat transfer. To determine amount of heat transfer to determine amount of heat transfer when specific heat capacity when specific heat capacity and temperature difference when specific heat capacity and temperature difference are known. When specific heat capacity and temperature difference are known. When specific heat capacity and temperature difference are known. Right? Okay. In front of the second equation, C theta. In front of C theta, write down to determine amount of heat transfer when heat capacity when heat capacity and temperature difference. Heat capacity and temperature difference. Heat capacity and temperature difference are known. Temperature difference are known. Don't worry about the meanings of specific heat capacity, temperature difference now, right? Because we'll be taking a deep dive into everything in the next part, right? So don't worry about the terms here, right? We'll be explaining everything today throughout this class, right? And Q equals ml. In front of Q equals ml, write down. In front of Q equals ml, write down. To determine amount of heat transfer, 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 in a state change, in a state change, in a state change. Video එකේ මොකක් හරි අවුලක් තියෙනවනේ. Give me 1 minute again. I think now it would be fine. Was it blinking? Was it blinking or something? I saw something like that in my preview. I think now it's fine. Right? So this last one, Q equals ml for the determination of amounts of heat transfer in state changes. So tell me, what is a state change? What is a state change? Speak up, speak up. What is a state change? So speaking up in the sense, speak up and put it to the chat. Hi, what is a state change? Tell me, what is a state change? I need these things from your side. What is a state change? Tell me. Students, what is a state change? As you know, Prashibhan, changing from solid to liquid to gas. Good. Correct. Very good. Very good. Right? But not limited to. It can change from ice. Just 1 minute. Okay. Due to temperature, one state change to another. Good. Good. And in that answer, there's something to be corrected. That is not due to temperature, but due to an amount of heat. Not due to temperature, but due to heat. Right? Due to heat. Okay, good. So I got what I wanted. Listen, a state change is, right, a change from any state to any state of a substance is a state change. It is not limited to solid to liquid to gas, right? Say it is from solid to gas at once, that is also a state change. Gas to solid at once, that is also a state change. So likewise, any kind of a change of state from solid to liquid to gas, from solid to liquid to gas, between solids, liquids, and gas is called a state change. It can be from solid to gas, or solid to liquid, or liquid to gas, right? Liquid to gas, or liquid to solid, or gas to liquid, or gas to solid, right? Anything is a state change. Anything is a state change, right? For such scenarios, Q equals ml and only Q equals ml is valid, right? Only Q equals ml is valid for such scenarios. Okay. Write down somewhere here within brackets. Here within brackets, write down. Any kind of a change, write down. Any kind of a change. Any kind of a change of states. Any kind of a change of states. Any kind of a change of states. Any kind of a change of states among solid, liquid, and gas. Among solid, liquid, and gas. Among solid, liquid, and gas. That is a state change. Okay. Listen now. First, we will be introducing all terms here. Right? First, we will be introducing all terms, and you are going to see what these meanings are. Right? Once these meanings are known, right? Once these meanings are known, only we can go to the rest, because there are a few more things to identify, and the definitions are also coming up. Identifying units, definitions, and some other things using these equations. Right. Listen now. Look at the board again. In all equations, look at here. In all equations, Q refers to amount of heat, right? Or heat transfer. Q, right? M, don't write M. M in all equations is mass, right? M in all equations is mass. Then S, specific heat capacity, where C is heat capacity. Two different things. We will see the difference in the coming part. And theta in all equations is not temperature, that is temperature difference, right? Even though we write it as theta, there is a difference, right? Delta theta, it is actually delta theta, but in the equation we are writing it as theta. I think you saw the same idea in expansion as well, right? Linear expansivity, equation of linear expansion, delta L equals L1 alpha theta. Delta L equals L1 alpha theta. Then where theta is not a temperature but a temperature difference. I stuck now. What's happening today? Now okay, right? I'm not sure what's wrong. There's nothing, nothing apparent because I checked everything. And the video is stuck through the streaming software, not Zoom, the camera streaming software. Video, not the camera, video streaming software. Okay, let's see. C is specific heat capacity, theta, temperature difference, right? And L here, right? L here, what is L? Specific latent heat. Specific latent heat. Okay, now introduce these terms one by one. Introduce these terms one by one. First one, Q. Q, write down Q. Amount of heat transfer. Q. Amount of heat transfer. Q. Amount of heat transfer. Then M. Mass. Simple M. Mass. Then S. Specific heat capacity. S. Specific heat capacity. S. Specific heat capacity. Next one, C. Heat capacity. C. Heat capacity. C. Heat capacity. Theta. Temperature difference. Theta. Temperature difference. Theta. Temperature difference. Right? L. Specific latent heat. 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 Okay. Now, let's start from this one. Let's start from this one. What is this? Specific heat capacity. As an next heading, write down. Next heading, definition of, write down. Definition of specific heat capacity. Write down. Definition of specific heat capacity. Definition of specific heat capacity. Okay. Now, if you are to define, right? If you are to define something, we know, right? If you are to define something, we know, we have to start from the equation and subject it before defining it. Okay. Write this equation and subject S. Write down the equation and subject S because we are going to define S. Within brackets, write down specific heat capacity. Within brackets, S. Within brackets, S. Subject S. Subject S. Then it gives, so we know Q equals ms0. Then S equals Q over ms. Right? Sorry, Q over m theta. Q over m theta. Q over m theta. Listen. So first, check whether the numerator and denominator has same dimensions. Because if they have same dimensions, we know always we are defining something as a ratio. If they have the same dimensions, we define it as a ratio. If they don't have same dimensions, always we defined as considering or by considering denominator terms as unit terms. By considering unit terms, denominator terms as unit terms. Right? So very recently, you saw this idea, in thermal expansion. And in reverse class also, very recently you saw that idea in both definitions we had for coefficient of viscosity and coefficient of surface tension. Right? In both cases, it was there. Right? So same thing. Now, their dimensions are different. Which means we have to go with that unit style now. Unit style. Considering denominator terms as unit values. Then this is a unit mass. This is a unit mass. Right. Since there is a unit mass, at once we can say, see, this is a unit mass, no? For a unit mass, at once we can say it has a 1 kilogram, no? Standard unit mass. And for theta, temperature difference, right? Temperature difference. And for unit temperature difference. For unit temperature difference, we can say 1 degree Celsius, no? Right? If there is a unit temperature difference, that is 1 degree Celsius. Right? And I told you that, right? I told you that in thermal physics, definitions are done only for temperature increments. When temperature increases, because in thermal, we have basically two scenarios as temperature increasing and temperature decreasing. All definitions are done only for the decreasing side. Sorry, only for the increasing side. Same thing as what we did in expansion. Right? Define karanne increasing ekada vidarai. Right? Okay. Subject is Q over m theta. Q over m theta. What is happening? What is happening? I'm not sure what is happening. I can't see any error messages or nothing like that. But the video is getting stuck. Okay. So subject is equals Q over m theta. Okay. Below this one, write down the definition in red. Below this one, write down the definition in red. Write down the definition in red. The required amount of heat the required amount of heat due to increase of temperature amount of heat required due to increase of temperature by 1 degree Celsius by 1 degrees Celsius of a substance of a substance of mass 1 kilogram of a substance of mass 1 kilogram of a substance of mass 1 kilogram is defined as specific heat capacity. Right. Same thing again. I think I might have to restart this laptop. Give me 2 minutes until the laptop is restarted, and until then, let me log into the meeting from the other laptop. What's wrong today?
Recording in progress.
Okay. 1 second. Let's check out whether there are any updates due. Because sometimes when the app is not up to date also, same thing is happening. No, it is updated. It says it is updated. 1 second, I'm going to restart this. Right. Let's see. So I wondered whether the settings are changed. Yeah, but I didn't notice any changes as well. No changes. Didn't notice in the sense there's no changes. What is wrong? Okay, now let's see again. So what I was telling was the definition here. Did I give you the definition? I gave, right? Definition I check. Check the definitions again. The required amount of heat. The required amount of heat. The required amount of heat to increase temperature by. Required amount of heat to increase temperature by 1 degree Celsius. Right? Unit temperature. No? Since there is unit temperature by 1 degree Celsius. By 1 degree Celsius of a substance of mass 1 kilogram of a substance of mass 1 kilogram of a substance of mass 1 kilogram. A unit mass, no? 1 kilogram is defined as is defined as specific is defined as specific heat capacity is defined as specific heat capacity, right? Is defined as specific heat capacity. Okay, now a small task. Listen, a small task. Listen, find units of specific heat capacity quickly and send me. Find units of specific heat capacity. Find units of specific heat capacity. Find units of specific heat capacity. Units. And send it here. Units of specific heat capacity. Anyone? What are the units? What are the units? Units of specific heat capacity. Please go to the main chat. Please put your answers to main chat, and the ones on YouTube, you also can answer. You can respond in the chat box. What are the units? Units of specific heat capacity. You know what are the units using to measure temperature differences that we discussed in expansions. Mostly correct. Good. Aida, your answer is correct. What else? What else? Anyone with different answers, different incidents? Send your answers, then I can see. Once you send your answers, I can see. Okay. First, tell me this. What is the unit of measuring temperature difference? First, tell me this. What is the unit of measuring temperature difference? Theta is also equal to delta theta. Tell me, what is the unit of measuring temperature difference? Respond my questions quickly. What is the unit of measuring temperature difference? What is the unit we use to measure temperature difference? We have the recent idea in expansion. Quickly. Again, don't wait too long until I keep asking. Quickly. No one? No one? There were two units. There were two units. We discussed there, right? It is either degree Celsius or Kelvins, right? Then S is Q over MS M theta, right? S is Q over M theta, right? Q over M theta. Then units of S is units of Q over units of M, units of theta. Units of Q is kilograms. Units of mass is, sorry, units of Q is joules. Units of mass is kilograms. And units of theta, degrees Celsius, right? Degrees Celsius. So it comes as joules per kilogram per degree Celsius, right? Or else, we can measure temperature difference using kelvins instead of degrees Celsius. So in that case, that is joules per kilogram per Kelvin. Both units are correct. Joules per kilogram per degree Celsius or joules per kilogram per Kelvin is also correct. I proved that temperature differences are same using both degree Celsius and Kelvins. Under expansion, same thing is applicable here. Since there is a temperature difference, both are fine. Right, take it down. Take it down. Degrees Celsius. Yeah, it is one of the units. Correct. It is one of the units. Right, take it down. Take down the units. Right. Write down below with a red pen in point form. First point. Write down below with a red pen in point form. First point. First point. Write down specific heat capacity. Write down specific heat capacity. Specific heat capacity is independent of specific heat capacity is independent of amount and shape. Amount and shape. Specific heat capacity is independent of amount and shape. Right? The idea is like this. Listen. The idea is like this. Now we all know the specific heat capacity of water is 4200. No, 4200. Then it doesn't matter in which shape that water is, right? For any shape, doesn't matter. That is 4200, and doesn't matter whether it's 1 kilogram of water or 500 grams of water or 1 milligram of water, 10 kilograms of water, doesn't matter, right? It is always 4200. So that's why I said specific heat capacity is independent of amount and shape. It is independent of amount and shape. Independent of amount and shape. Right. Second point. Write down. Keep using red. Keep using red. Second point. A substance having a substance having a substance a substance having a substance having a substance having a comparatively higher specific heat capacity, a comparatively higher specific heat capacity, a substance having comparatively higher specific heat capacity means it changes its temperature, means it changes its temperature, it changes its temperature, it changes its temperature slowly, it changes its temperature slowly under a given amount of heat. It changes its temperature slowly under a given amount of heat. Under given amount of heat. Right? Within brackets write down, within brackets write down. Within brackets write down. Difficult to change temperature. Right? Within brackets, difficult to change temperature. Difficult to change temperature. Difficult to change temperature. Difficult to change temperature. Right, next point. Next point, write down. A popular example is water. A popular example is water. Third point. A popular example is water. Right? Within brackets write down. Within brackets write down. Within brackets write down. Water is a good coolant. Right? Water is a good coolant liquid. Coolant. Water is a good coolant liquid. Water is a good coolant liquid because of this. Water is a good coolant liquid because of this. Water is a good coolant liquid. Coolant. Water is a good coolant liquid because of this. Okay, let's move on. As the next heading, write down definition of heat capacity. Definition of heat capacity. Write down definition of heat capacity. Take down the equation and subject heat capacity. Q equals C theta. So we need C. C is Q over theta. C is Q over theta. Right? Q over theta. C is Q over theta. Q over theta. Listen. Dimensions are different. Dimensions are different. Since dimensions are different, we will be defining this as unit terms. And this is only theta, right? So this is for a unit increase of temperature. A unit increase means an increase by 1 degree Celsius. A unit increase means an increase by 1 degree Celsius. It's clear now? Okay, write down below with a red pen. This is a definition. Write down the definition in red. Write down the definition in red. Write down the required amount of heat. The required amount of heat. The required amount of heat. The required amount of heat To increase temperature, to increase temperature, to increase temperature, to increase temperature, by 1 degree Celsius, to increase temperature by 1 degrees Celsius, to increase temperature by 1 degrees Celsius of a substance, of a substance, of a substance is defined as, is defined as, is defined as, is defined as heat capacity, is defined as heat capacity, is defined as heat capacity. Okay, a small task again. Find units of heat capacity. Find units of heat capacity. What are the answers? Right. Say, says Q over theta, no? Units of Q of over units of theta. Right? Units of Q is, that is a heat energy. Heat is an energy. Joules. Right? Theta degrees Celsius. Theta degrees Celsius. Then it gives joules per degree Celsius. Right? Or if someone measures temperature in kelvins, it gives joules per Kelvin. Take down both. Take down both. Okay. As an next heading, write down next heading. Relationship between, write down. Relationship between relationship between relationship between specific heat capacity and relationship between specific heat capacity and heat capacity relationship between specific heat capacity and heat capacity relationship between specific heat capacity and heat capacity. Okay, a small task again. Listen, and once I gave you time, you can quickly do this. Listen. Now you know two equations which has specific heat capacity and heat capacity. No, right? Consider those two equations and try to do something. Something in the sense can be a division, multiplication, subtraction, addition, substitution, right? Or anything like that. Anything like that. And get me a relationship among, right? Get me a relationship among C, Sn, C, Sn, M. Right? Quickly. Get a relationship among those three. You can send what you got here. And you can send what you got here. C equals ms. Good. C equals ms. Yes, good. Right? Very straightforward. Very straightforward. We know from the first equation, we know Q can be written as ms theta. Right? Where Q is amount of heat transfer, M mass, S specific heat capacity, and theta temperature difference. Theta is not a temperature, that is temperature difference. Right. So let's assume this as equation 1. And on the other hand, we know same Q can be written as C theta. Same Q can be written as C theta. Right. Now, if we consider the same temperature difference, Q equals Q, no? Q equals Q. From this side, Q equals mh theta. From this, that is C theta. Theta cancels. Right. So it gives C equals ms. C equals ms. Highlight to square this. C equals ms. Highlight to square this. Okay. Let's check this out now. Look at here. About specific heat capacity, we know. About specific heat capacity, we know. A specific heat capacity is independent of both shape and the amount. specific heat capacity is independent of both shape and the amount. Shape and the amount. Now, C is ms. C is ms. Where S is a constant value. S is constant for a given material. S is constant for a given material, and that is independent of amount and shape. But C is a function of m, no? C is a function of m, which means C is going to change with simple m. C is going to change with mass. C is changing with mass. C is changing with mass. Then heat capacity of 100 grams is different from heat capacity of 200 grams. That is different from heat capacity of 500 grams. That is different to heat capacity of 1 kilogram. That is different to heat capacity of 5 kilograms. That is different to heat capacity of 10 kilograms. Likewise, C, it depends on amount. C depends on amount, but S doesn't. C depends on amount. C depends on amount, right? As well, it depends on shape as well, right? It depends on shape as well. Because when shape changes, also there are changes in masses, volumes, right? So when it changes, it also changes, right? Copy it down up to here and highlight or square this C equals ms and write down below with a red pen. First point. Write down below with a red pen. First point. First point. Write down heat capacity. Heat capacity depends on heat capacity depends on heat capacity depends on shape and amount of substance. Heat capacity depends on shape and amount. Heat capacity depends on shape and amount. Heat capacity depends on shape and amount of substance. Heat capacity depends on shape and amount of substance. Heat capacity depends on shape and amount of substance. Right? Underline, no highlight, shape and amount. Underline, no highlight, shape and amount. Underline, no highlight, shape and amount. Second point. When amount changes, second point. When amount changes, when amount changes, mass changes. 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 Hence, heat capacity changes. Hence, heat capacity changes. Hence, heat capacity changes. Next point, keep using red. Next point, keep using red. Both Q equals ms theta. Both Q equals ms theta. Both Q equals ms theta and Q equals C theta. 。  . 。  . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 。 . 。 。 . 。 。 . 。 。 . 。 。 。 . . 。 。 . 。 。 . 。 。 . 。 。 . . 。 . 。 . 。 and Q equals C theta. Cannot be applied, cannot be applied, cannot be applied cannot be applied for state changes, cannot be applied for state changes, cannot be applied for state changes. It is only applicable, it is only applicable it is only applicable, it is only applicable for temperature differences. It is only applicable for, it is only applicable for temperature differences. It is only applicable, it is only applicable for temperature differences. It is only applicable for temperature differences. Within brackets, write down, within brackets, no change of temperature, no change of temperature, within brackets, no change of temperature, no change of temperature, no change of temperature for a state change, no change of temperature for a state change. 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 Right? Highlight or underline that part. No change of temperature for a state change. Highlight or underline that. Right. Okay. Listen. Now next we are going to move on to the remaining one, only remaining one to be defined. That is specific latent heat. That is specific latent heat. Right. Now in this first part, after understanding definitions, right, we will be slightly moving on to the application types and the usages of these equations, right? And by the end of today, my plan is to cover all theory parts, right? Finish off all theory parts regarding calorimetry. So next day we can start all the applications, question types on calorimetry, right? That's the plan. That's the basic plan, right? So next heading, write down definition of, next heading, definition of specific latent heat. 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 Specific latent heat. Okay. Write down the equation again and subject L. Write down the equation and subject L. Q equals ml. So L is given by Q over M. L is given by Q over M. L is given by Q over M. Right? Check units and dimensions again. They are different. Since they are different, we are going to define this as a unit denominator style. Right? Ratio to write a ratio, we have to have same units and dimensions in numerator and denominator. Right? Now we can make this a unit term and do the definition. Right? Most importantly, in this equation, we don't have a temperature difference term included. Right? So in this equation, we don't have a temperature difference term included. We don't have temperature difference term. We have a term එකක් නැහැ. Right? Which means the exact idea behind this is there won't be any temperature difference. There won't be any temperature difference in a state change. Right? That's why there's no theta term here. There won't be any temperature difference in a state change. Any state change occurs at a given temperature, given in the sense a constant temperature. Now, as an example, right, you know, melting of ice. No, when ice melts to water, it happens at zero only. It happens at zero only. Otherwise, it is not going to be at 1 or 2 or, and during the process also it is not going to change the temperature. Ice starts to melt at 0 and it completes melting also at 0. And when it comes to say water to gas, water to water vapor, gas means water vapor. No? So if you are boiling some water, at 100 degrees Celsius, it will reach the boiling point. So at the boiling point, until the whole amount of water is converted into gas, into vapor, all the system remains at 100. If there is a temperature change will occur upon the completion of a state change only. Right? It is not going to change the temperature in the middle of a state change. Always state change will be completed first, and then only if there is a temperature difference, then only the temperature will increase or decrease. Got the idea? Right. So that's why there is no heat term here. There is no temperature difference. Okay, let's write down the definition first. Write down the definition in red. Write down the definition in red. Write down the definition in red. Write down the required amount of heat. The required amount of heat. The required amount of heat. The required amount of heat to change state from to change states of a substance from, sorry, to change the state from a substance from, to change the state of a substance, to change the state of a substance, to change the state of a substance, to change the state of a substance from one to another, 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 for mass of 1 kg, of a mass of 1 kg, of a mass of 1 kg at constant temperature, at constant temperature, at constant temperature, at constant temperature, at constant temperature is defined as defined as specific specific latent heat is defined as a specific latent heat. Underline or highlight at constant temperature again. Underline or highlight at constant temperature again. That is very much important, right? Any state change occurs only at a constant temperature. Any state change occurs only at a constant temperature, right? Underline or highlight at constant temperature. Okay, now a small task again. Find units of L. Find units of specific latent heat. Find units of specific latent heat. Find units of specific latent heat. Right? Listen. There's only one unit for that, right? That is units of Q or units of M. Q is measured in that's amount of heat, joules, and M is measured in kilograms. So this is joules per kilogram. Joules per kilogram. Joules per kilogram. There's only one unit. Joules per kilogram. Right. Listen now. Listen. This is the general definition of. This was the general definition of specific latent heat. Listen, something important. This is the general definition of specific latent heat. Now, using this, based on this, we are going to define the specific latent heats of fusion and vaporization, because fusion and vaporization are the most popular two state changes we have, right? What is fusion? What is fusion? Anyone? What is a state change in a fusion? What is a state change in a fusion? What is it? Huh? What is a state change in a fusion? Two things, two specific ones, important ones: fusion and vaporization. Fusion and vaporization. What is fusion? Liquid to solid? No. No. Liquid to solid is called condensation. Liquid to solid is called condensation. Condensation. solid to liquid. Yeah, it is solid to liquid, right? Solid to liquid. Does that happen again? All right. So still that is not 100% fixed. What the other case? Let's see. I don't see any apparent thing. Okay. Yeah, that is a solid to liquid. Solid to liquid. Liquid to solid is called condensation. Condensation, right? Okay. What is vaporization? Let's identify them one by one. Fusion is the state change from solid to liquid. Okay. Vaporization. Vaporization. What about vaporization? What is the state change in vaporization? Liquid to gas. Liquid to gas. That you know, right? Liquid to gas. Liquid to gas. Liquid to gas. Now, at which point, as a temperature, at which point a fusion takes place? As which point? Solid to liquid. එහෙම conversion එකක් වෙන්නේ මොන temperature එකද? At which point a conversion like solid to liquid happens, occurs? What do we call it? Anyone? At which temperature this occurs? Fusion. As a point, as a temperature. At which temperature fusion occurs? Melting point. Good. Melting point, no? That is called the melting point. This temperature is called melting point. Melting point. And this temperature is called vaporization occurs at? Vaporization occurs at boiling point. Right? So that is called boiling point. Right. Now, listen. This is what we are going to do. We have the general definition here. No? We have the general definition here. General definition of a specific latent heat. Now we are going to specify this definition to vaporization and fusion. We are going to specify this to vaporization and fusion. Right? Only two words are going to change in the general definition. Only two words. One is, right? Now in general definition, I said you the state changes from one to another. No. Now in the specific ones, we have to say from which state to which state specifically. And I said you that is at constant temperature. So when there is at constant temperature, you have to say, right, which point is that constant temperature. Those are the only two. That's the only two differences. Right. So when you study also, listen, when you study also, you can keep in mind the general definition. You can keep in mind the general definition. Right. Now if fusion or vaporization is asked, then you can specify using these two words in that particular definition. That's why. That's how. That's very easy. Right? Okay. Write down as the next heading. Write down definition of a specific latent heat of fusion. Next heading. Definition of a specific latent heat of fusion. Write down definition of specific latent heat of fusion. Definition of a specific latent heat of fusion. Definition of specific latent heat of fusion. Okay. Again, write down the equation and subject L. Write down the equation and subject L. It will be same like this. Do it. Write down the equation and subject L. It is same. It is same. Right. Now let's move on to the definition. Write down the definition in red again. Write down the definition in red again. When it comes to questions, listen. When it comes to questions, any definition from these definitions can be asked. Right. And about latent heats, more frequently, the specific latent heats for vaporization or fusion are asked, not the general definition. right? Usually, general definition won't be asked. Instead, the specific latent heats of fusion or vaporization can be asked, right? So in past papers in the history also that has been come, but when you study, it is a little bit easier, much easier to keep the general definition in mind, right? And convert it to your respective one once you got the requirement, once you have the need, right? Okay, write down below in red again the required amount of heat. Write down the required amount of heat, the required amount of heat, the required amount of heat to change the state from, to change the state from, to change the state from here fusion Nemedian fusion from solid to liquid, from solid to liquid S2L, from solid to liquid, from solid to liquid of a substance, from solid to liquid of a substance, from solid to liquid of a substance of mass 1 kilogram, of a substance of mass 1 kilogram, of a mass 1 kilogram at melting point, at melting point, at melting point is defined as, at melting point is defined as, at melting point is defined as specific latent heat, is defined as specific latent heat, is defined as a specific latent heat of fusion, defined as a specific latent heat of fusion, right? Next heading, next heading, next heading, write down definition of specific latent heat of vaporization. Next heading, definition of specific latent heat of vaporization, definition of specific latent heat of vaporization, definition of specific latent heat of vaporization, definition of specific latent heat of vaporization. Okay, now I will give you like 2 minutes. You can do the definition there, right? I have mentioned the important points here. Okay, write it down, very easy, write it down. Raise your hand once you finish writing the definition. So again, only 2 words are going to change. Follow the same thing we followed in the fusion. Follow the same thing we followed in the fusion. Nora, check your WhatsApp. I'll send you. Okay. See, same thing. Same thing again. Only two words are going to change. Nora, it's clear, right? So probably it might be a mistake. Mistake by the chemistry teacher, right? Otherwise, that's how it should be. Okay. See, again, definition of a specific latent heat of vaporization. Only two words are going to change, right? So it should be check your answers, check your definition. Answers in the sense, yeah, okay. Answers means your definition. Check it. The required amount of heat. The required amount of heat to change state from liquid to gas. To change state from liquid to gas. To change state from liquid to gas. To change state from liquid to gas of a substance of 1 kilogram. Of a substance of mass 1 kilogram at boiling point. At boiling point. At boiling point is defined as a specific latent heat of vaporization. Is defined as a specific latent heat of vaporization. Is defined as a specific latent heat of vaporization. Right? Specific latent heat of vaporization. Right. From first definition, underline no highlight, solid to liquid and melting point. In the first definition, in the first definition of fusion, underline no highlight, solid to liquid and melting point. Underline no highlight, solid to liquid and melting point. Solid, liquid and melting point. From this definition, in the second definition, underline no highlight, liquid to gas. Underline no highlight, liquid to gas. Liquid to gas and boiling point. Liquid to gas and boiling point. Listen now. Listen. Listen. Don't write, listen. Usually, a specific latent heat of vaporization. Usually, specific latent heat of vaporization of any material is greater than that of fusion. Is greater than that of fusion, right? Because now if you are doing chemistry, right, now if we need to break these bonds, right, break these bonds, energy should be given, right? Now breaking a bond between a solid and a liquid state is comparatively easier compared to breaking the bond between the liquid and gas states, right? That's why L vaporization, specific latent heat of vaporization, is always greater than that of fusion, right? Now as an example, consider water. Now fusion of water is from ice to water. No, fusion of water is from ice to water. And on the other hand, compare liquid to gas means vaporization of water, boiling of water, right? If needed, you can try this out at home. Take the same amount of ice. Say you have ice cube of 100 grams, right? Say you have a ice cube of 100 grams, and supply some heat and let it melt. Right? Even if there is kept at the atmosphere also, it melts, no, because that the small amount of heat is also enough. That small amount of heat is also enough to do that state change, because the melting point of water is 0, no? So therefore that's enough. But to boil it, we have to keep on our cooker or whatever the burner, right? Whatever the burner, for a longer time compared to melting because of this. So it takes longer. Boiling takes longer time. Boiling in the sense vaporization. Vaporization takes longer time compared to fusion. Fusion means melting. Right? Fusion and melting are two same words. They are equal. They are synonyms. Right. So therefore, this is valid for any kind of a substance. Keep that in mind always. Vaporization is higher. Okay. Write down in red. Don't write this. Write down this point in red. Write down specific latent heat of vaporization. Write down specific latent heat of vaporization. Specific latent heat of vaporization is higher than specific latent heat of is higher than specific latent heat of is higher than specific latent heat of fusion. Specific latent heat of fusion for any substance. 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 Any substance. For any substance. For any substance. Okay. Now take this down and highlight or square this. Take this down. Okay. Next point, keep using red. Next point, keep using red. Next point, next asterisk mark, keep using red. There's no temperature difference. There's no temperature difference. There's no temperature difference. There's no temperature difference at any kind of at any kind of, there's no temperature difference at any kind of state change. There's no temperature difference at any kind of state change. Right? There's no temperature difference at any kind of state change. For the same sentence, same point at this, whole system is at a constant temperature. 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 Throughout the process of state change. 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 Okay. Now, let's see an example how this these things are applicable. How these things we learn are applicable. Okay. Any questions up to here? Or is it all clear? Raise your hand if it's clear up to this point. We didn't do much in the sense we did only few definitions and equation identifications. Right. Okay. Let's see an example. Write down. Example one. As example one, write down. Determine amount of heat required. Determine amount of heat required. Determine amount of heat required. Determine amount of heat required to vaporize 2 kilograms of water. To vaporize 2 kilograms of water. To vaporize 2 kilograms of water at 30 degrees Celsius. To vaporize 2 kilograms of water at 30 degrees Celsius. 2 kilograms of water at 30 degrees Celsius. 2 kilograms of water at 30 degrees Celsius. Okay. And these data are given. Write down. First point, specific latent heat. Specific heat capacity. Specific heat capacity of water. Specific heat capacity of water. Write down 4,200 joules per kilogram per degree Celsius. Second point, specific latent heat of vaporization of water. Specific latent heat of vaporization of water. specific latent heat of vaporization of water. 2 times 10 to the power 6 joules per kilogram. Take it down. 2 times 10 to the power 6 joules per kilogram. Okay. Now stop all your work and look at here. See what is going to happen. Initially, we have 2 kilograms of water at 30 degrees Celsius. 2 kilograms of water at 30. 2 kilograms of water at 30. Fine. Now, initially, see, we have, look at here, water at 30 degrees Celsius. Right? And 2 kilograms. First tell me, listen, now you have to respond. First tell me, our final target is vaporization. No? At which point vaporization is going to occur? At which point vaporization is going to occur? Which point? Boiling or melting? Boiling point. Right? Boiling point. What is the boiling point of water? What is the boiling point of water? As a value? What is the boiling point of water? 100 degrees Celsius, no? Right? 100. 100 degrees Celsius. That is 100. That is 100. Then, now initially my water is at 30. In order to start vaporization, first all the water particles here, all the water molecules here should be taken to 100 degrees Celsius. Otherwise, it is not going to do part by part because the state change is something occurs at a constant temperature. Then first of all the particles should be taken to that constant temperature. Then only all particles undergo, all molecules undergo their state change. Right? So therefore, first of all, this water at 30 should be taken to, see, water at 30 should be taken to water at 100 degrees Celsius. Water at 30 should be taken to water at 100 degrees Celsius. Right. Now, at this point, we have water but at 100 degrees Celsius. We have water but at 100 degrees Celsius. Now, this water should be converted into vapor, into gas. Right. Now, here, then hereafter, this should be converted to vapor. Right. There will be same 2 kilograms of vapor. That is also at 100 degrees Celsius. Because there's no change of temperature, there's no change in temperature in a state change. There's no change in temperature in a state change. Right? I asked to vaporize only to vaporize. Then now at this point, our process is finished. Right? Before applying equations, first identify which equations are applicable for each part. First identify which equations are applicable for each part. Okay. See, look at here. This is a temperature difference. This is a temperature difference. For temperature differences, we have two options. Either Q equals ms theta or C theta. But look at here, I have given you the specific heat capacity of water. Since specific heat capacity is given, you can't go with C theta. C is not given. Only specific heat capacity is given. Right? Then you can find this out. Let's say this amount of heat required here is Q1. You can find this out using ms theta. Right? And here, this is a state change. Right? Since there is a state change, we know there's only one option left. Right? One option available actually for a state change. There are no more options. There is only one option for a state change. That is ml. Right. Now, since we have selected, we have chosen equations. Now, to calculate these amounts of heat required, right? Heat requirement, we can apply these equations and do a simplification. Say, do a calculation. Simplification in the sense, we can do a calculation like this. See, now let's say amount of heat required for this process is Q. Then there are two processes happening. One is from water at 100, sorry, from water at 30 degrees Celsius to water at 100 degrees Celsius. The amount of heat required is Q1, we assume. And second process is water of 100 degrees Celsius is converted to wave at 100 degrees Celsius. The amount of heat required is, let's say, Q2. Right? Now, do a simplification. Q1 is ms theta plus Q2 is ml. Same mass, no? Take 2 out. And S here is 4200. Theta is not temperature, that is temperature difference. Temperature difference between 30 and 100 is 30 and 100 is 70. Plus M is taken out, sorry, M is taken out, then L is 2 times 10 to the power 6. 2 times 10 to the power 6. Right? Simplify this. Once it is simplified, right, I will let you do the simplification. Once it is simplified, we can get the amount of heat required for this process. There are two processes to be completed, right? Then for each process, we have found this, we have substituted the requirements of heat, right, as ms theta and ml. Choosing the correct equation is up to us. Then you have to check whether it's a temperature difference or a state change or what it is, and you have to correctly pick the equation and use it where necessary. Got it? Simplify and send me final answers. And you can raise if any questions. You can raise if any questions. Raise if any questions. Any questions? Okay. Can you explain again? I'll explain again. Right. First, take it down and do the calculation. So before moving on to the next question, I'll explain again. First, send me your answers, values you got. Any values? A field has got the value. Others, you also can check your value whether it's aligned with the with that value, and you also can send your answers. Okay, let's see. Right now, from here, I can see 10 to the power 3 is common. No? So take that out. Then 2 times 10 to the power 3. 10 to the power 3 is common. So here 42 into 7 remains. Plus here if 10 to the power 3 is taken out, 10 to the power 3 is taken out, which means 2000 remains. 2000 remains. Q equals 2 times 10 to the power 3. 2 times 10 to the power 3. 42 into 7. What's the value? 40 times 7 is 280, no? And 2 times 7 is 14. Then 294. 294. Oh, 294. Then this is 294 plus 2000. So Q equals, we'll do here, Q equals 2 times 10 to the power 3. This is 2294. 2294. Right. Then final answer 2 times 2294. 294 එක කියලා කියන්නේ 600 592 94 sorry 588 588 නේ හරි 588. Then this is 4588 10 to the power 3 joules. 4588 10 to the power 3 joules. Yeah, I feel your answer is correct. Your answer is correct. Okay, others take it down if you didn't get the answer. Take it down. Today I'll be giving the break around 6:10 because some of the Muslim students requested that their praying time has changed and now it's somewhere around 6:10. So therefore we'll be taking the break today at 6:10. Otherwise, my usual time is like between 5:50 to 60, somewhere around. Take it down. I will give you another example to try by your own. Right, take it down first. Write down below with the red pen. Write down below with the red pen. Write down below with the red pen. Determine a point, red pen. Determine required amounts of heat. Determine required amounts of heat. Determine required amounts of heat. Determine required amounts of heat for each step. For each step slash process. For each step slash process. For each step slash process. For each step slash process using relevant equations using relevant equations, using relevant equations, using relevant equations. Using relevant equations. Okay, right. So let's do another example. You can ask if anything before moving on. You can ask if anything before moving on. If there's no questions, we will move on to the next example. Raise your hand if you understood this. And let me explain again before moving on. Since someone asked. See? Okay. Good. So again, for one last time, listen again. First, identify the processes, right? When the example is given, in the question is given, identify the processes, right? Initially, we had water at 30 degrees Celsius, right? 2 kg of water at 30, no? Initially, we had water at 30 degrees Celsius, right? So before undergoing the state change, right? All the molecules should reach the respective temperature. All the molecules of the substance, all the particles, all the molecules of the substance should reach the respective boiling or melting point, respective temperature. So therefore, from 30 to 100, right, first thing is from 30 to 100, its temperature should be increased. From 30 to 100, its temperature should be increased, right? So once the temperature is increased, here what we have is, there is still water, right? Still we have this in the water state, water, but temperature is at 100 now. Since each and every molecule is at 100, now only we can do the state change, right? Then when this is at 100, to whole 2 kg is at 100, then we can do the state change to convert this water to water vapor. Right? And both the states at the state change should be at the same temperature. And I explained it before as well, because there is no change in temperature in any kind of a state change. There is no change in temperature in any kind of a state change. Then once the system is at 100, then this can be converted into water vapor at 100 degrees Celsius. And when you are choosing equations, if there are temperature differences, we have two options, Q equals ms theta and g theta. Since specific heat capacity is given, go ahead with ms theta, right? And for a state change, there's only one equation, right? There is only one equation, that is Q equals ml, right? These two data provided, right? So is it clear now? If any questions, ask again. Now it's clear, right? Okay, and before moving on, as another point, as the next point, using red, write down again. As another point, using red, write down again. All molecules of substance all molecules of substance should be taken to 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 the required temperature should be taken to the required temperature should be taken to the required temperature within brackets melting point or boiling point within brackets melting point or boiling point. Within brackets, melting point or boiling point. Melting point or boiling point. Melting point or boiling point. Before starting, melting point or boiling point. Before starting, melting point or boiling point. Before starting, the state change. Before starting, the state change. Before starting, the state change. Before starting the state change. Before starting the state change. Okay, right. Let's try another example. Write down example 2. Right, take down this as example 2. Example 2. Right. Listen. Example 2. Write down. Write down. Example 2. Write down. Determine amount of heat to be supplied. 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 Amount of heat to be supplied. To convert 5 kilograms of ice. 5 kilograms of ice. 5 kilograms of ice. 5 kilograms of ice at minus 20 degrees Celsius. To convert 5 kilograms of ice at minus 20 degrees Celsius to water vapor to water vapor at 150 degrees Celsius. Water vapor at 150 degrees Celsius. Water vapor at 150 degrees Celsius. Take this down, these two. Right. And other than that, specific heat capacity of water is here. Specific latent heat of vaporization of water is here. Next one, specific heat capacity. Write down. Specific heat capacity of ice. 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 given 2000 joules per kilogram per degree Celsius. Then write down a specific heat capacity of steam. Specific heat capacity of steam. Steam 2100 joules per kilogram. Now let's consider it also as 2000 for the ease of simplification. 2000, right? Then specific latent heat, last one, specific latent heat of fusion, specific latent heat of fusion of ice, specific latent heat of fusion of ice, specific latent heat of fusion of ice. Three times 10 to the power 5 joules per kilogram. Right. These data are provided. 1, 2, 3, 4, 5. Right. These data are provided. So based on these given data, listen. Based on these given data, try to find this. Now I need to convert 5 kilograms of ice at minus 22, water vapor at 150. Right. Process you can first write down the process starting from 5 kilograms of ice at minus 20 up to water vapor means steam, water vapor at 150. Give it a try. Wait. Shall we do something for the ease of simplification? Let's consider this as 4000. Let's consider this also as 4000. Then it will simplify faster. Consider specific heat capacity of water as 4000 here. Consider specific heat capacity of water as 4000. Right? Okay. And this is not 200, 2000. 2000. Correct. Check your values again. 4000, 2 times 10 to the power 6, 2000, 2000, 3 times 10 to the power 5. Okay, start now. Right? Raise if any questions. Okay, listen. Since it's 6 now, right? And since they need to pray around 6:10, we'll take the break now. Right, listen. We'll take the break now. You can complete the calculation during the break. Right, I will take this discussion after the break. So let's break for 15 minutes and come back. Right, let's break for 15 minutes and come back. Now it is 6:07. 6:07. So we'll be back at 6:22. Right. So if you are not going anywhere, you can complete the calculation during the break. If not, you can go out and refresh yourself and come back. Let's regroup by 6:22, right? Right. Okay. I'm audible again, right? Okay, any answers? Any answers you got for this? Any answers you got for this one? Anyone? Anyone? Any answers you got for this one? Send your answers. No? Okay, let's first identify the process. Listen. Now let's identify the process. Listen, look at here. Let's identify the process. We are starting at 5 kilograms of ice at minus 20. Right, 5 kilograms of ice at minus 20. Before I explain, let me ask the question that way, this way. How many different processes you got? The ones who have tried, tell me how many different processes you got from this to this. How many different processes you got from this to this? How many processes you got? 2, 3, 5, 6, 7. So likewise, how many processes you got? How many different processes you got? On YouTube? No idea? Anyone has a confidence? Anyone has confidence with your answer? Or anyone is confident enough? You can put it to the chat. If you are like 100% sure, and if you are 100% confident about like your number of processes, no? Okay, let's say starting from 5 kilograms of ice at minus 20. So initially we have, let me start from here. Initially we have ice. Initially ice 5 kilograms, right? That is at minus 20, right? So immediate next thing to do for ice is we have to take this minus 20 ice cube at minus 20 to 0, because at 0 only the state change can occur. At 0 only the state change can occur. Then initially from here to 0, see, this ice cube should be taken, right, to 0, right, 0 degrees Celsius. And at 0 only, we can do the state change. At 0 only you can do the state change. Then at 0, you can convert it to water. Then what at 0 should be taken to? What at 0 should be taken to? What at 100? What at 100? And what at 100 should be converted to steam at 100, and steam at 100 should be heated up to steam at 150, right? So how many processes? Say this is Q1, Q1, Q2, Q3, Q4, Q5. 5 different processes. 5 different processes. These are temperature difference. Temperature difference. SC is given. So this can be found using ms theta. This is a state change, ml. These are temperature difference again, ms theta. Right? These are state change, ml. These are temperature difference again, ms theta. Right? Okay. Now I have helped you out with the process. Listen, I have helped you out with the process. Same 5 kilograms remains same throughout. Same 5 kilograms remains same throughout. No? Right. Now you can check your process with mine and make your changes if anything, rectify it if anything, and now do the calculation and send me the final answer. Now I have helped you with the process. When the process is known, that is only a simplification. When the process is known, that is only a simplification. Just a simplification. Simplify it. Most of the 5 scenarios. Yes, good. 5 scenarios. Yeah, 5 processes. 5 processes. Correct. Good. Now this is a plug and play. Then the final answer. Sorry. Just a plug and play. Anyone? Now this is only a simplification. Simplify and get it. Now before I do, right? Nothing to add there. Right? Nothing to add. Okay, let's see. Time is enough. Time is enough. This is a small calculation. 1 second. Okay, see. Then total Q equals, take 5 out, right? 5 is common now. Take that 5 out. Here, from here to here, there is a ms theta, right? S of ice. Now, this process is for ice, no? Ice undergoes this process, ice. Then, the specific heat capacity of ice, 2000. Specific heat capacity of ice, 2000 into theta minus 20 to 0, temperature difference is 20. Temperature difference is 20, right? Plus M is taken out, Q2, ice to water, fusion. Ice to water, fusion. Make up that. This is fusion. And water to steam, here we have vaporization. So fusion. Specific latent heat of fusion of ice, 3 times 10 to the power 5. So this is 3 times 10 to the power 5 plus ms theta again, S of water, water from 0 to water from 100. S of water, specific heat capacity of water, 4000. 4000, right? Theta 100, theta 100, temperature difference plus vaporization. M is taken out, L of vaporization, specific latent heat of vaporization of water, 2 times 10 to the power 6, 2 times 10 to the power 6 plus ms theta, steam from 100 to 150, steam, S of steam, specific heat capacity of steam, specific heat capacity of steam, 2000. Temperature difference, 50. Now, if you simplified these numbers, right? If you simplified these numbers, right? That's it. If you simplified these numbers, that's it. Right. 10 to the power 4 is common throughout, right? Yeah. 10 to the power 4 is common. So first I'm going to take 10 to the power 4 out. Then 5 times 10 to the power 4. When it is out, 10 to the power 4, only 4 remains here. Plus 10 to the power 4 is out, 30 remains here. 30 remains here. 10 to the power 4 is out, 40 remains here. Plus 10 to the power 4 is out, 200 remains here. 10 to the power 4 is out, then 100. 10 to the power 4 is out, 100 remains here. Sorry, 10, 10, sorry. 10 remains here. Okay, simplify. That's it. 4 plus 30, 34. 34 plus 40, 74. 74 plus 200, 274, 284. Then 5 times 284 times 10 to the power 4. 5 times 284. What's the value? 1420. 1420. 1420. 10 to the power 4 joules. Right? So we can keep this as, right? We can keep this as 14.2 into 10 to the power 6 joules, no? 14.2 10 to the power 6 joules. 10 to the power 6 is mega. Then this is 14.2 megajoules. 14.2 megajoules. Right? A simple calculation. Focus on the processes we have. Focus on the processes we have. 14.2 megajoules. Right? Check your simplifications and take down if any changes and ask if any questions. And ask if any questions. Write it down. Okay. Raise your hand if this sum is clear, if this example is clear. Raise your hand if the example is clear. 2, 3, 5, no, 4, 5. Is that all? 6. Okay. 7. Okay. Right. It's clear. Same thing as I did before. Identify the process and do the math for each process. Then you have to pick the correct equation, correct in the sense the relevant equation where necessary with your process, with respect to your process, Right, okay. Let's move on. Let's move on. Let's move on. See, another important fact. Listen. Another important fact. Another important fact. Important fact. Listen. Listen. However, Now we know uh, the values of specific latent heats of fusion and ice of fusion and vaporization of water, right? If we just compare those values, it is more than 6 times of ice. It is more than 6 times of ice. Now, as an example, we knew these two now from the previous calculation. Specific latent heat of fusion was 3 times 10 to the 5 joules per kilogram, right? Whereas specific latent heat of vaporization was 6 times, 2 times 10 to the power 6, 2 times 10 to the power 6 joules per kilogram, right? See the ratio. You can get the ratio and see L of vaporization to L of fusion. L of vaporization is 2 times 10 to the power 6. L of fusion is 3 times 10 to the power 5. These two cancels. This is 20 over 3. 20 over 3, around 6.67. Around 6.67. Right, in water, this is the difference it has. This is the difference it has. The idea is, say under the same rate of heat flow, it took only 10 minutes to melt the ice cube, melt an ice cube of 1 kilogram. It took only 10 minutes to melt an ice cube of 1 kilogram. To vaporize the same amount of water, 1 kilogram of water you got from the ice cube, it takes minimum 10 times 6 minutes to do that, roughly, right? 10 times 6 minutes. Again, 1 hour. It takes like 1 hour, 60 minutes, 1 hour to do the vaporization. That's the idea. That's the idea. Because higher the specific latent heat, higher the amount of heat that you need to supply, right? Then higher the time it takes if there is under constant rate. Therefore, with that, time and everything changes, right? Difficulty, time, everything changes. Okay. As an important note, important fact, write down. As an important fact, write down below. Specific latent heat of vaporization of water. Write down. Specific latent heat of vaporization of water. 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 Specific latent heat of vaporization of water is approximately 6 times. Is approximately 6 times. Is approximately 6 times that of fusion. Is approximately 6 times that of fusion. Is approximately 6 times that of fusion. Okay, take it down. Take this down. Take it down. right? Okay, let's move on. Let's move on. Okay, let's move on. Listen. Now, if I draw a temperature variation for the previous process I considered, see, if I draw a temperature variation, right? Temperature variation. For the previous process, right? For the previous process, which means, for example, 2, I'm going to draw the temperature variation, right? I'm going to explain temperature variations by using the same example I gave you before, right? From example 2, right? A temperature variation is, listen, a temperature variation is variation of temperature against time. Variation of temperature of the object, of the substance against time, right? Now for that, we have to use our graphing knowledge a little bit. Right? So we know Q equals ms theta, no? See, Q equals ms theta. See, Q equals ms theta. To include time into this, let's divide both sides by time. Right? No problem, no? Because I have divided both sides of the equation by time. I need to create time. Q over T. Q over T is power, no? Q over T is power. Then if I label this as power, this is ms theta over T. My y-axis is theta. Subject theta. Theta equals P over ms. T. X-axis is T. See? Now this is our X. Whatever it is as a constant, as a product with X is gradient and theta is Y. See, it is going to follow Y equals mx. It is going to follow Y equals mx. Right? So therefore, when you are trying to plot ms theta, it follows Y equals mx like this. And let's assume P is the power as constant because that's a given rate, right? And M is anyway constant. And with S, you can see the gradient changes. See, gradient of graph is P over ms, no? Gradient of graph is P over ms. Gradient. Therefore, gradient equals P over ms. When S decreases, what about gradient? Gradient increases. When S decreases, gradient increases. Increasing gradient means increasing tan alpha, which means increasing slope. Clear? Okay, now having that idea in mind, now we are starting at minus 20. So we are starting at minus 20. Let me start somewhere here. Otherwise, I'll run out of space. Let me start somewhere here. Right. So we are starting at minus 20, and this is at degree Celsius. And time is in seconds, right? Minus 20. Then minus 22, you know what happens. Then you know what happens. So likewise, now we know the process from the beginning to the end. We'll give you 2 minutes before I start. Try this out. And you have to take this down. Now this is the logic I use for ms theta when plotting ms theta. Two minutes. Anyone? Finished? Okay. See? Let's see. Let's start. First part. First process is minus 22. 0 no? Minus 22, 0. That is ms theta. ms theta. ms theta. ms theta. ms theta means it is going to follow y equals mx. That we have proved. It is going to follow y equals mx. Right? So it is linear. My idea is this is linear. 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 Since there is linear, from here to here, the graph is linear. And it is reaching 0 at this point. So at 0, it is going to undergo the state change. It is going to undergo the state change. At a state change, temperature is constant. At a state change, temperature is constant. Then here, it is constant at 0. It remains constant at 0. It remains constant at 0. And now it should be heated up until 100, no? Until 100. Until 100. And check this again. Listen, check this again. A specific heat capacity of ice source 2000 and a specific heat capacity of water is 4000. It is higher. Higher means lower gradient. Right? It's a lower gradient. Then compared to this should be a little bit lower gradient. Right? Compared to this, a little bit lower gradient. Increasing up to 100. Right? Now for this one, only the rough shape is enough. Right? But this gradient should be visible from your graph you are plotting. Right? A lower gradient. And now at 100 again, the other state change. At 100, another state change. Right? Now if the time takes for this one is this much, for here the time should be greater than that, higher than that. Because a higher latent heat, no? That's a higher latent heat. Let me erase this. That is a higher specific latent heat. Therefore, time is higher. Time is higher. It is approximately 6 times. But at least you have to show that the time taken for this process should be higher. Something like this. Approximately that is 6 times. Okay, then again from here to 150, here to 150, 150, again ms theta, right, like this. So that is where the process is going to end. Got it? This state change is, this is from ice to water, and in this phase there is only ice. This is ice to water. In this phase this is water. Here water to vapor, and here this is only vapor. Is it clear? So likewise, we should be able to draw temperature variations as well. Right? More questions are coming up next day. Right? I just gave you an idea what is coming up, what is ahead of us. Okay, take it down, and ask if any questions. So logically, you have to argue and plot this. Right? Argue kar lende, logically argue kar lende, argue it and plot it. Take it down, and you can ask if anything. You can ask if anything. Take it down quickly. Okay, raise your hand if you got this. Raise your hand if you got this. Got in the sense if you understood this. Raise your hand if you understood. Okay, right, good. Right, so there are more questions coming up. Get the idea. Get the idea. We can do these kind of things as well. See these phases, then you can clearly understand what's happening here. Initially we had ice, then from here to here there is only ice. This is a state change, ice to water. This is water, water to water vapor, or we can say steam, and this is a steam, water vapor. Right, let's move on. Let's move on. Let's move on. Right, erasing. Next heading. Next heading. Another very important and interesting theory part. Right, another important and very interesting theory part. Write down next heading. Anomalous expansion of water. Anomalous expansion of water. Write down. Okay. Again, tell me. Let's break this down. Anomalous expansion of water. Break this down. Let's break it down. Tell me, what is the meaning of word anomalous? Anomalous. What does that mean by anomalous? So we know what expansion of order is. We know what expansion of order is. What is anomalous? What is anomalous? Anyone? Anyone? What is the meaning? Anomalous. If you have heard the word before, what's the meaning? Anomalous. Anyone? Anomalous. YouTube? No? Anomalous. Huh? No? What is the meaning? Anomalous. No idea. Listen, listen. Anomalous means not the standard way or not the proper way, not the standard way. Deviating from the standard, deviating from the proper scenario, or deviating from what is to be expected. Deviation from what is to be expected is called anomalous. It is called anomalous, right? No one has said, right? Anomalous means deviating from standard, deviating from standard. That is called an anomalous scenario, deviating from standard, right? Now, as an example, listen, as an example, let's say you are going to school by bus on daily basis. Listen. This is an example. You are going to school by bus on daily basis, right? And on a particular day, say you went to the school by train, So that is an anomalous behavior, because usually you have been traveling to the school by bus, but on a particular day, you took the train to travel to the school, right? So that day that you traveled using train is an anomalous day, right? In your routine, there is an anomalous one, something like that. That is called an anomalous scenario. Anomalous, right? Keep that in mind. Okay, now anomalous expansion of order. It is like this. Now we are connecting this, we are linking this with the expansion theories we learned. Tell me, if temperature increases of an object, if temperature of an object increases, what can you say about volume? Volume increases or decreases? Volume. Quickly. Volume increases or decreases? Increases or decreases? Expansion, volume expansion. Tell me. Natural behavior of any expansion, any object, any expansion is when temperature increases, it increases. Because, right? Because, very simple, we have finished expansions. Delta V is V1 gamma theta, right? Or else we can do the same using this V2 equals G1 1 plus gamma theta. When temperature increases, V2 increases. So when temperature increases, volume increases. When temperature increases, volume increases, right? But density decreases. Why? Because in density expansion, rho 2 equals rho 1 over 1 plus gamma theta. Density expansion. When temperature increases, density decreases. But when temperature increases, volume increases, right? So when temperature increases, volume increases, but density decreases. That is a standard behavior. That's a normal behavior. Normal, right? Anomalous means abnormal. Anomalous means abnormal. Not normal, abnormal. Right? That is what I meant by deviating from standard. abnormal, abnormal, not the normal, right? So normally any substance increases its volume and decreasing density when temperature increases. But water in a specific region from 0 to 4 degrees Celsius, it behaves exactly opposite to this. It behaves exactly opposite to this, right? That behavior is called anomalous expansion of water. Anomalous expansion means that's an abnormal expansion, right? Write down first point under the topic, under the heading, write down first point. When temperature increases, write down, when temperature increases, when temperature increases, when temperature increases, volume increases, volume increases, volume increases, and density decreases, volume increases, and density decreases, volume increases, and density decreases of a typical substance, 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 of a typical substance. Next point. Sorry, before that, take this down. Take this down now. From this I argued, take this down. Relevant to that point, take it down. This is how volume increases and density decreases. Right, we have seen all the equations, we have done all the equations in expansions. Take it down. Second point, take it down. Okay, second point. As a second point, write down second point. But when temperature increases, volume decreases. But when temperature increases, volume decreases. Volume decreases, and density increases, and density increases, and density increases of water, of water, of water between, of water between 0 to 4 degrees Celsius. Between 0 to 4 degrees Celsius. Between 0 to 4 degrees Celsius. Right? 0 to 4 degrees Celsius. This is called, this is called, this is called, this is called anomalous expansion of water. This is called anomalous expansion of water. This is called anomalous expansion of water. Right? This is called anomalous expansion of water. This is called anomalous expansion of water. Okay, right? As the next heading, write down next heading, variation between volume and temperature. Variation between volume and temperature of water. Variation between volume and temperature of water. Right? Volume and temperature of water. Right, look at here. Volume and temperature. Volume and temperature. Right. Listen, look at here. This is 0 degrees Celsius. And let's say This is 4 degrees Celsius. Now, anomalous expansion of water is only between 0 and 4, right? That is not everywhere. Anomalous expansion is only between 0 and 4. Then before 0, it behaves totally normal. Before 0, it behaves totally normal, right? Before 0, it behaves totally normal. Normal scenario is when temperature increases, volume increases. Then when temperature increases, its volume increases. When temperature increases, its volume increases, right? And after 4 also, right? Listen, after 4 also, it is normal. Between 0 and 4, this is only between 0 and 4. After 4 also, it is normal, right? It is normal. Normal scenario is when temperature increases, volume increases. Normal scenario, right? Anomalous expansion is between only 0 and 4. Now let's see what happens. One thing about the volume, right? One thing about the volume, another special scenario, special case when it comes to water is it's changing its volume and density when it undergo the state change also. No? Because as an example, before 0, what you have is ice, right? Before 0, now in this side, look at here, this side you have ice, this side we have ice, and this side we have water, right? We know density of ice is 900, but density of water is 1000, right? So what has happened when ice converts to water, right? When ice converts to water, its density increases. Its density increases. Density increases means volume decreases. Density increases and volume increases. Volume decreases. Then at here, there's a small drop, a sudden drop due to what? A sudden drop due to this. Sudden drop of volume due to this. Because when ice converts to water, it reduces volume. Now, between 0 and 4, the opposite scenario of this. When temperature increases, still volume decreases. When temperature increases, still the volume decreases like this. And this part is totally normal. It increases. Got it? So, only this region is called the anomalous expansion. Right? Only this region is called the anomalous expansion. It behaves abnormal. It behaves deviating from the normal scenario. Anomalous expansion. Take this down. And for your understanding, this is due to state change. This is due to state change. This is state change. What is that state change? Ice to water, no? Fusion. That is due to fusion. Right? And only this part is anomalous expansion. Take it down. This is very interesting thing about water, right? And this kind of a behavior is only with water. That's why we discuss about it separately. Write down quickly. Be it very much clear to you, right? The graph is very important. In past papers also it has come, right? Already it has come, and it will be coming in the future as well. right? Write down below with a red pen, right? Take down everything here and write down below with a red pen with an asterisk mark. With an asterisk mark. Water behaves. Water behaves. Water behaves normally. Water behaves normally. Water behaves normally as a typical substance. Water behaves normally as a typical substance. Water behaves normally as a typical substance before 0 degrees Celsius and before 0 degrees Celsius and before 0 degrees Celsius and after 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 4 degrees Celsius. Before 0 degrees Celsius and after 4 degrees Celsius. Right? Okay, then write down next heading, right? Same thing, we are going to draw the variation for density. Right, write down variation between density and temperature of water. Variation between density and temperature of water. Sorry. Variation between density and temperature of water. Same thing. Density and temperature. This is density now. Let's say this is 40 degrees Celsius, 0. What is the normal behavior? See, normal behavior is when temperature increases, density decreases. When temperature increases, density decreases. Then before 0, it behaves totally normal. Before 0, it behaves totally normal. Right? And after 4 also, it should behave totally normal. After 4 also, it should behave totally normal like this. After 4 also, it should behave normal. Right? Now, about this thing. See, about this thing. Happens at 0 state change. When ice becomes water, density increases. Then because of that, there should be a sudden increase here. Sudden increase here because of this state change. Like this. A sudden increase. Because it is increasing from 900 to 1000, no? This is due to what? Fusion. Fusion. Right? Now, between 0 and 4, the abnormal behavior, anomalous behavior is even when the temperature increases from 0 to 4, even when the temperature increases from 0 to 4, density increases. Density increases. Then from here to here, density increases. Right? Let me draw a nice curve here. See? So even when temperature increases, density increases, and then after 4, it behaves normal again. Right? So this phenomenon is called anomalous expansion of water. Because of the expansion, density is also affected. Right? Take it down. You have to know both curves for volume and density. Have to know both. Have to know both curves for volume and density. Take it down. Right, write down below with a red pen again, a point. Right, write down this point below the graph with a red pen, put an asterisk mark and write down water takes, water takes, water takes, water takes, water takes its minimum volume. Water takes its minimum volume. Water takes its minimum volume. Water takes its minimum volume and maximum density. Minimum volume and maximum density. Water takes its minimum volume and maximum density at 4 degrees Celsius. At 4 degrees Celsius. At 4 degrees Celsius. Right. So that is something we can see from the graph. Right. Maximum volume and minimum, sorry, maximum density and minimum volume. Right. This is called anomalous expansion of water. Listen. Listen. Right. Now, from here, listen. From here, all the theory parts here in calorimetry is done. So next day we will be starting all application types of calorimetry. Right. Next day, first thing is applications. Right, of calorimetry. Right, and then we can finish all applications of calorimetry by next day. Right, and the next week we will be starting the next part. There's another part of that is going with calorimetry as convection. Right, so we will be starting convection parts in the next week after the coming one. For immediate next week, our plan is finishing calorimetry. By the next week, by immediate next week, we will be finishing calorimetry, and the day after, the week after next week, right? Week after next week, we will be starting convection and Newton's law of cooling. Right? Those are the parts coming up during the month of February, and as I told you, tomorrow we'll be having the next S2A discussion. I think it's 4, right? Day 4, 5, day 4, I guess. Day 4 of S2A discussions. Next day, sorry, tomorrow, and next day of next Saturday of the reverse class, we'll be starting elasticity. Right, and on Monday, discussion of paper 9. Right, now there are more things, and we are 26 weeks ahead of the exam. Right, 26 weeks and exactly now Thursday is also gone. No, exactly 3 days. 26 weeks and 3 days ahead of the exam. Right. Okay, any questions? Any questions from the things we discussed today? Or is it all clear? Put it to chat to raise your hand if there is clear, or put a thumbs up. All clear? Yeah, raise your hand or put it to the chat. What about the ones on YouTube? Are you also all clear? The ones on YT? Right. All right then. All right. Then if no questions, we'll wind up. Keep that in mind. We are 26 weeks ahead of the exam, 26 weeks and 3 days. Right. So study hard. Give your fullest. Right. Give your fullest effort. Give your maximum. Then you will get that effort, get that sacrifice in return with the results. Right. Okay then. Then see you again in the next class. Stay safe and work hard. Right. Good night and goodbye.